All right. Today we're hoping to start and finish chapter 2. It's only got 2 sections in it. I'm on chapter 2, chapter 7. What we're doing in chapter 7 is we're going to be estimating parameters and describing sample sizes or determining sample sizes, because you can't really do an experiment until you know how big your sample is supposed to be. So if you're going to analyze the entire population of the United States, you can't do it with 100 people. So we're going to look at what determines a valid sample size for you to work with. What we've been doing so far, we've looked at, just hit me, yeah. We've looked at descriptive. I always keep on moving it. We look at descriptive statistics. So what do you think descriptive statistics is? What do you think descriptive means? Describing, yeah, because you have the data, you're describing what the data tells you. Now we're going to something called inferential statistics. Well, we're going to infer the population information, the population mean, population variance, population deviation. So because it's too expensive a lot of times to sample the entire population, so that's what we usually end up doing that. But in case we have to do it, we're going to look at now inferential statistics. Unfortunately, because of time restraints, we're only going to deal with the first 2 sections of descriptive statistics of population mean and a population proportion. Proportion simply means the ratio of it, how big it is with respect to what you're looking for. All right, so the first thing we have to look at are some key points. We have to describe our terminology. We're first going to look at the term point estimate. The point estimate, the sample proportion divided by P is the best point estimate single value estimate of the population proportion. So it's P hat. So we're trying to take the single, it's a sample proportion, P hat. It's a single value that estimates the population proportion. Once we do that, we've talked about these before, but now we're going to look at even further, is the confidence interval. The confidence interval is, we'll have to pick a value to see how confident we are that the data will fall within a certain parameter range, which we've used those to find, we looked at those as critical values. So the confidence interval is depending on how big you want your tails to be. Those are of the confidence interval that the confidence endpoints that defines our confidence interval. Then we're going to look at the sample size. What size is needed? To create a valid approximation of the population. Our notation. Our little x, as always, has been the number of successes. N is the sample size. Capital N is the population size. Remember, lowercase is samples, uppercase is population. P, this is called a hat. P hat is the sample proportion. It's made up of x over n, and the little p is the population proportion. Which is whatever we have over capital N this time. Our population's capital. All right. So let's start putting these formulas together. The point estimate. Remember, the point estimate is the value that we're going to use to estimate the population. So we're going to have p hat. Won't do that just yet. We've already discussed the definition enough. We know the formula. It's n over or x over n. All right, let's look at example one, or example. The chapter problem. Okay, our chapter problem. What was our chapter problem? I didn't print it out. Oh, here's this. Chapter problem is this. The window of evolving technologies. Importance of surveys. That's a title. In our relatively new data-driven world, it is essential that we have the ability to analyze and understand the polls and surveys that play a critical role in guiding just about every facet of our lives. This chapter presents the tools for developing the ability. Listed below are some recent surveys that focus on evolving technologies. It doesn't take much imagination to recognize that each of these surveys reveals results with serious implications. First one, Pearson survey. 59% of Gen Z respondents for ages 14 to 23 identify YouTube as a preferred learning tool. good enough for professors because that's where they get their information. How accurate is it? It's horrible because nobody verifies it. Anybody can put anything they want to do, and people believe it. Actually, there are a bunch of people who put these experiments on there saying that if you put battery acid and baking soda together, it'll blow up. You probably go blind. Or in the National Center for Health Statistics survey of 16,113 subjects, 53.9% of them lived in homes with no landline phones. Actually, it's a little more now because you don't need a landline. It's a home phone. You don't need those anymore because you have your cell phone. You're almost never home. The mobile banking study of 2,000 adults said that 91% prefer using an app for banking instead of going to a physical bank. That's pretty bad because if your phone ever gets stolen or anything like that, there goes all your banking information. You just made it easier for them. In a Sallie Mae survey of 950 undergraduate students, 53% take online courses. And that's growing every day because the way that a lot of professors are doing, they don't teach online. They just watch these videos and that's it. There's no classes. So it's getting worse and worse. In a Society of Human Resource Management survey, 3,490 human resource professionals, of them, 60% of employers offered telecommuting to employees. Telecommuting is working from home. Yeah, of course, I work from home. But then again, what is that going to show you? You don't need your big building anymore. And then you find out you don't need half the people anymore either. Biometric security. In the USA Today survey of 510 people, 53% said that we should replace passwords with biometric security, such as fingerprints, eye scans, face recognition. So if you have biometrics, a fingerprint, and you ever burn your finger or you lose your finger, you're locked out of everything. There's always a good bet to everything. Because surveys are now so pervasive and extensive, and because they often accepted without question, that's what I have questions about all of those, we should analyze them by considering issues such as the following. What method was used for the survey subjects? How do we use the sample results to estimate the values of the population parameters? How accurate are survey sample results? Typical media reports about surveys are missing an extremely important element of relevant information. What is usually missing? Well, they're missing sample size, they're missing the location, the demographics. It's a whole bunch of information that's missing. How do we correctly interpret survey results? Unless it's in a professional journal, don't believe them. Because look at all these right here. It said, this one here, 53% of the surveys says that we should take biometrics. 53%, that's a big number. But it's only over 510 people. So you're looking at 255 people. Out of the nation, out of the world, it's very, very small. So that's what I'm saying is we don't know much about these things. It's what they usually publish are these percentages. They don't tell us the rest of the stuff. Where did you select this? Did you get a sampling from young people to old people, or just middle-aged people? The other surveys all involve sound sampling methods. So with these surveys, we can proceed to consider other issues listed above. Okay. So that means now example 1, online courses. It says, the chapter problem included reference to a Sallie Mae survey of 950 undergrad students. And 53% take online courses. This is the first thing we have to define. What is an online course? Is it a correspondence course where you do everything yourself? An online class is where instead of being in a classroom, you're at your computer, where the instructor lectures for an hour and 20 minutes from their computer. That's an online course. Or if you're doing the work yourself and never see it and never hear from the teacher, that's a correspondence course. Or is it hybrid, where you could do it from home or you could do it from class? So we have to first define what do they mean by online courses. So I said, based on the results, find the best point estimate of the proportion of all undergrads taking online courses. This is the question. Notice how the question is set up our parameters. It tells us what we're looking for, the best point estimate. Is it of a population or is it of a sample? So since there are 950 people, it's a sample.
Population.
It's a sample. Because how many undergraduate students are there in the world? So we're doing a sample. If we're using best point estimate, we're using a sample to predict the population. Because this is only 950 students. That's not even 1 year of students at Mountain View. So that's a very, very small number. And then it says, okay, of the proportion of the sample of all undergraduates taking online courses. So our formula is this. How many students are taking these courses? Well, we know that P is 53%. So which one of these two numbers do we know? So we know that, yeah. We don't know how many, so we know this. The sample size is 950. So we can go 0.53 equals X over 950. Multiply 950 to both sides. So 950 times 0.53. That tells us the number of students taking online courses. That it's going to be, well, half of 950 is 525 or 475. So a couple more. So what this tells us, since this is a best point estimate, remember that the population, the sample estimate is a good guess for the population. So the best point estimate is P equals point or 53% or P equals 0.53. That's a pretty straightforward one. Again, best point estimate is the best point estimate is we're estimating the population from the sample. Next thing we're gonna talk about the confidence interval. Why do we need to know confidence interval? What does it say on our sheet? Yeah, but since we don't know exactly how much it is, then we have to have an interval. We have to have an interval from a low point to a high point where we're going to be a certain percent accurate, sure that the number is going to fall within there, that the population value will fall between there. So let's say this was our confidence interval was 10 to 50, and we had a 90% confidence interval. What this says is we are 90% sure that whatever our averages, our deviation, it's going to be between those two numbers. The population one's going to be between those two numbers. We're 90% confident. The higher this number is, the closer the values come together. Usually, it doesn't always happen. So the confidence interval is a range of values used to estimate the true value of the population. Because remember, all we're doing now in this chapter is estimating the population from the samples. And we're not given most of the information. The confidence level. Is the alpha. Usually the alpha are used to be 85%, 90%, 95%, or 99%. It's just how confident are you that your answers are going to say that the population is between these levels, these intervals. So we use those. And in this course, we mostly use 95, but sometimes we use 90. So the confidence is a probability one minus alpha such that the confidence interval actually does contain the population parameter. Okay, well, there's a little bit more to it. When we say population parameter, what that usually means is the mean, variance, deviation. Those are the parameters that we're looking at. So what we're doing here is the confidence level, which one we pick, is the probability such that the confidence interval that they're going to find out actually does contain the population parameter. Now, here's an assumption. Assuming The estimation process is repeated a large number of times. That's the law of large numbers. For example, we talked about earlier is if we all know that the number 3 on one die happens 1/6 of the time. How many times do we have to roll it so that it does become 1/6 of the time? We can't roll it once because if it doesn't work, then it's 0%. We roll it twice, we can have a 0, we can have 100%, or we can have 50%. So we have to have a large number of times, law of large numbers. Also known as the degree of confidence or the confidence coefficient. Because it tells us how sure are we that it works? Because so when we look at this thing, we have a bell curve. Let's say our critical value is here. This is what usually happens, and this is what we're looking for. So we're confidence, let's just say we have an alpha of 90%. That's 0.90. So one of two things can happen. Well, remember the formula we have here is 1 minus alpha. So our probability is 1 minus alpha, or 1 minus 0.9, which is 0.10. So this is our level of confidence. Because this will mean a lot more when we talk about these two parts, because when we do an experiment, we make a guess what's going to happen. We've got a hypothesis. That hypothesis is either going to work or it's not going to work. So if it works, it's great. If it doesn't work, then we have to have another value for it. So that's where we're going to define those as well as null hypothesis and alternate hypothesis. So whatever your alpha is, the confidence value, the confidence coefficient of confidence is 1 minus alpha. And I gave you a chart there. So for example, if your alpha was 99%, then what you would do is convert that to decimals, which is 0.99, move decimal 2 to the left, which makes it 0.01. So yeah, that's what I'm saying is that's why they call it, one of the reasons why they use the word confidence is how sure are you of this? So if your experiment doesn't work at 99%, then you go down to 95% confidence. If that doesn't work, then go down to 90%. If that doesn't work, go down to 85%. That's what actually usually anything below 90 is much of a guess. So, but this is how, again, when you read these things in magazines or articles and stuff or anything like that, they have to tell us what level of confidence they use. Because the smaller that number, the less confidence they were. The critical value, or CV. So we talked about this earlier. It's the z-score on the outer bounds of a bell curve that separate the significantly high and low regions. From the remainder of the data or values. And that's what we did last time. We found usually we found this way, where the critical values are here. And when we talked about the mean, it was the mean minus 2 standard deviations, the mean plus 2 standard deviations. Then we also talked about it as this was 1.95% and this was 1.95%. So we had plus or minus 1.95% for the confidence level. So to find this, remember, alpha is your level of confidence. To find this one, we have to take alpha over 2. So we have, say, 0.10. And that means that both sides are 0.05. Why is that important? Because what we're doing here we have to find the z-scores. Why the z-scores? That's all we know so far. And the z-score, the table tells us what percent is to the left of that. So we can find this part here. We can find this one here and subtract it from 1. Alpha 2. And then we also find everything in between. So this one here is z alpha 2 minus z alpha 1. That gives you that area. The area of those. And on the bottom of your page, just show you we have a 95% confidence interval. These are called tails. So when you have an experiment like this is a two-tailed test, which is why we have to take our alpha and divide by 2. If we only have a one-tailed test, we only want either to the right or to the left. Those are called one-tailed tests. So what that says is the area of both sides, our confidence level is 95. Remember, it's 1 minus alpha. This is our alpha value. 1 minus alpha gives us 0.05. Divide that by 2. Half of 0.05 is 0.025. And then the cumulative area is your 97.5. So that says, what does this really tell us? What that tells us here is this. So let's say our confidence level, we're 95% confidence. And we have a two-tailed test. So 1 minus alpha, 1 minus 0.95 is equal to 0.05. Since it's two tails, we take alpha over 2, which makes it 0.05 over 2 makes it 0.025. So what that means is 0.025 it's in there and 0.025 it's there. So if it's not in this one, where the other part is this whole area here. So what is 100 minus 0.025? 0.975. So this is, remember, since we're looking at 95%, we have 5% left over. And half of 5% is 2.5. So this becomes 97.5%. That's how confident we're going to be it's going to happen in there. So what this is saying here is our confidence level. This tells us is 95% that the population will fall within there. Because remember, whenever you do an experiment, you're trying to prove what's not normal, what doesn't normally happen. This is what normally happens. Since you're saying that the current population average falls within 95%, we're looking at what happens on the other 0.025%. So look at our charts. We have a confidence level. We're going to have our what level we're looking at. The 1 minus, this is 1 minus alpha. This is our Z alpha over 2. We're doing for two tests, two tails. So we have 90%, 95%, and 99%. So what's our alpha for 90%? 0.10, because it's 1 minus 0.9 is 0.10. This is 0.95. So 1 minus 0.95 is 0.05. This is 0.99. 1 minus 0.99 is 0.01. So this is the sum of both tails. Now we got to find the z-score of each tail individually. So that's why we got to do the divided by 2. So we take 0.10 divided by 2, we get 0.05. Remember the formula to find our Z values?
So, Professor, our confidence level is the N.
What do you mean N?
Is
It's
1
alpha.
minus alpha.
Right.
That's the critical value.
No, the
1
confidence level, the 1 minus alpha, this gives us our Z
0.10.
value.
Yeah.
Right.
So, yes, that's what I'm asking. So, the 0.1 is the critical value. That's N.
Oh, yeah. Yes,
The
this
critical
helps us
value.
find the
Divided
critical
by
value
2.
is a Z value.
Yeah. So,
We now
that's
have to
N divided
remember,
by 2.
this is the area.
Okay.
This is the area of the tails.
Mm-hmm.
So what this says is this. Between our critical values, we know that 90% of the data will be here.
Okay.
So that means with this one and this one equals 10%.
10%. Okay.
So this one is 5%. This one is 5%.
5%. Okay. Okay.
So what we want to know, what is the Z value of these two guys?
So the Z value is what I'm asking at to get the N over, is it N over 2 or alpha over 2?
Alpha over 2.
Oh, okay. So the
Simply
alpha,
because we have two tails.
yeah, because we have two tails. Okay.
Right.
So the alpha is going to be the result we get from 1 minus alpha. You know, we got 0.10 from 1 minus alpha. So
Right
the
here.
answer we get here, we're going to divide it by 2 to get the critical value.
Yes.
All right. Thank you. That's what I want to know.
Yeah. So we take the alpha and divide it by the number of tails.
All right. Thank you. I got it.
Yes. Yeah. Because if you have a two-tailed test,
Yes.
well, in a two-tailed test, typically two-tailed test is if you are saying that the population mean equals some number inside this 90%. So how do you prove that wrong? What's opposite of that is it doesn't equal. So if it's not 90% here, then it's got to be in one of these two places. It could be above it or it could be below it.
Okay.
Okay.
All right, sir. Thank you.
So what we have to do now is we have to look for Z of 0.05. And where do we find that? Right chart. And that one is right in the middle. Because, okay, since this is 95%, I mean 90%, this is 5%. So this one starts off at 95 and goes to 100%. This one starts off at 5 and goes down to 0. Because these 5 and these 5 equal 10%, and the rest of it's there. So our Z value is we have to find the value what Z value has a value of 95%. So we have to look at our chart. look everywhere until you see 0.95. Here's 0.495 here and 0.505. So 0.95 is right there. So what that tells us, 0.95 is equal to 1.645. So this value here is 1.645. That's our Z value. So let's do the same thing now with this next one.
Professor,
That
we have 1.65. Where did you get the 4?
Look at your chart. When I hold this thing up to the screen, take a look at it. We have 0.95.
Yes.
What does that equal?
1.645. Okay.
That's where I got it from.
Okay. Thank you.
So I do the same thing here now. I take 0.05 divided by 2. That gives us 0.025. What that means, remember, we have 95% of our data falls within this, which means these together. So this starts at 96, goes to 100.
100.
This one starts at
90.
no, this is no, but notice these are the last 5 numbers. So so this is 90, or this is 2.5 to 0.
So, Professor, whatever is on the left, because it's a negative, so it has to be from that point we get there, which is 2.5, to 0.
Right. So start off at 0, and you add your first 2.5. Then it starts at there. Our 95% has to be here. So 95 plus 2.5 is 97.5
5.
to 100. So this is 2.5 plus 95 is 97.5. And then this goes all the way to 100.
The one on top, the first one you did on top.
Yeah, this should be to 10.
Oh,
No, or this one should be 5, because this is 5 to 95 to 100. Where I got those numbers from is right here. Since 90, 1 minus 90 is 0.10, divided by 2, both sides have to
0.05.
be 5% of the data. So that's from 0 to 5 plus 90 in the last 5. Same thing here. So 1 minus 95 is 5 divided by 2. So this is from 0 to 2.5 plus 95. So let's look at, we have to find both of these values now. Or let's look at that one, 97.5. Or in decimal, it's 0.9750. 0.9750. Yeah, so here's 1.9750. It is 1.96. So this Z value is 1.96. Likewise, now for 99%. That gives us 0.1. 0.01 divided by 2 is 0.005. So that means for this one, This is from 0 to 0.5 plus 99. So it's 99.5 to 100. So we have to look at for the number 0.995. Just our luck. Whenever you see these lines here, that's a good indication, because it tells us if you're looking for 0.9950, then that's going to be 2.575. So that's how we find our Z values. So far, so good. What if we're looking for an 80% confidence level? I'll put the steps down. Steps to find the critical value Z alpha over 2. First, change the confidence level to decimal. So we're saying 80%. We're going to go down to 0.80. Second, your alpha is what's difference. Or 1 minus 0.8, which is 0.2. So alpha equals 0.2. We need to know this is because now to find our critical value, we need Z of alpha over 2. So divide alpha by 2, which is 0.2 divided by 2, which is 0.1. Find the values along the horizontal axis. So this is Z1, this is Z2. We know that 80% is in here. Convert that to percent. So from 0 to 10 is in here. Plus 80 equals 90 to 100. So we want this value here to be 90%, which becomes 0.9000. Find 0.9000 inside this Z chart. So 0.9000. Here we have 0.8997, 0.9015. Which one's closer? It's pretty much in the middle. So take both of those, divide by 2. So this one is 1.2. Yeah, so it's going to be 1.28 and 1.29. And divide by 2. So it's 1.285. That is your critical value. For Z equals 80/2. Or alpha over 2, which is 0.20/2. Well, we should get the same answer, but this one here would be negative since it's to the left of the mean. So we'll use the positive chart. This area and this area have to be the same. So. Okay, so whenever we do that, remember, we're estimating the population from a sample. Whenever we do that, we have to find what's called the margin of error, which is E. Margin of error, it tells us that and actually think about it, this is what we found out the critical values last time was we went once we find the error, we take it from our mean, add and subtract it. That's why we get mu plus or minus E. And sometimes it'll be recorded like this. Sometimes your margin of error will be recorded as an interval like that. Remember, we're estimating a population from the sample. And it represents the maximum how do you spell likeliness? Likeliness of the error amount. By error, how far the population parameter is from our sample population or parameter It's the difference of how far they are apart. Our formula. We have our two-tailed z-test times the square root of our population values. Remember what P and Q represented?
Parameter.
Of success and failure. So it's, and what does this number represent? Which we just found out in this chart. It's our critical value. And this number is our S. Standard deviation of our sample proportions. Okay, also I gave you, now, why is the standard deviation? Our mean. Yes, our population mean. So critical value tells us our values, our endpoints. Now, how far is it from there? So give or take this amount. Interpreting confidence intervals. There is a correct interpretation, many different creative incorrect interpretations. If we have this confidence interval here, 0.49 is less than P, our population, our sample, our population average is less than 0.562. The correct way, this is how you'd state it. We are 95% confident that the interval from this to this actually does contain the true value of the population proportion. That's the way you would do it. So what wrong ways? There is a 95% chance that the true value will be between there and there. It's incorrect to say it that way, but that's how it's mostly stated. But yeah, we are 95% confident that the interval, instead of saying we're 95% sure that the P is between there and there. It sounds like the same thing. But it's saying it's wrong because P is a fixed number and not a random variable. Can't move around. But this is the most common way of people saying it. 95% of sample proportions with tails between, no, that's way wrong. Because it's stating all this stuff that tails from, who knows what tails are. So this is an obvious wrong one. This is a correct one. So when you do your answers, put them in that format. Confidence level of success. The process. what it tells us here is this. How often are we correct, pretty much? What does that represent? 0.5 represents what in fraction? A half. So what we're saying here is
50%.
50%, right? Actually, yeah, this would be 50%, but move it 2 decimal points over it. So for a 95% confidence interval, we can assume a proportion value of p equals 0.5, which means it will be right most 5% of the time. Now, key elements. Now we're going to estimate population proportions. Population proportion. P. Here's our notation that we're going to use. The P, remember, that's our population. The P hat is the sample proportion. N is the number of samples. E is your margin of error. Remember, E equals and then your Z alpha over 2 is your critical value. So those are the values we're going to be using. So in order to estimate a population proportion, some things have to exist before we could be properties. The samples are simple random samples. In other words, you can't put any thought behind it. It just has to happen. Just collect the data. Binomial distribution conditions must be satisfied. Fixed number of trials. Trials are independent only two possible outcomes. Probabilities of each event is the same. We talked about this in the last chapter when we did binomial distributions. So there has to be a fixed number of trials, has to be finite, it can't be infinite. The trials are independent. What does that mean? One event doesn't affect the other events. Only two outcomes are possible. And each event has the same number, the same probability of occurring. Yeah, so from here on out, we're gonna have a lot of examples and stuff, which we have, before we do anything, we have to make sure, go through a checklist. Does this exist? We can use this method. If this doesn't exist, then we have to use another checklist. So if any one of those don't exist, we can't use that method. We gotta use something else. The confidence interval estimation of P, or population estimate, or population proportion, yeah, so we have to deal with any alternatives there. And the margin of error, E. The confidence interval estimation of P and the margin of error. So remember, we're looking from the population proportion. What do we create with our, we collect data and we run through, we create a sample. That's P hat. So we have our P hat will be on both sides. Minus our standard error and then plus our standard error. Remember, and our error formula was our critical value times the sample endpoints, the square root of it. Yeah, this is the formula used for this value. And we'd find, we'd do our calculations, we come up with our sample proportion, like we did earlier in the beginning with those number of students taking online courses. That's what that would give us. Then we calculate the margin of error, and we add and subtract that value. So this is what we'd use. Round to 3 significant digits. And here's our steps. To construct a confidence interval for P. Always, first step, check that the requirements are satisfied. The requirements are fixed number of trials, independent, two possible outcomes, and the probabilities are the same. Find your Z over 2, your critical values. Find E in that formula. Find P minus E minus mu, or minus P minus P hat plus E. And then round off your results. Check for appropriateness. Is it going to work? Is it feasible? Is it within that or is it not? So let's take example 2. And these are always going to be the steps whenever we do any probability analysis. Online courses. Construct a confidence interval. So in the chapter problem, we noted the Sallie Mae that deals with the student loans. 950 students, undergraduates. 53% of them take online courses. One, find the margin of error corresponding to a 95% confidence level. Find the 95% confidence interval containing P. Can we safely conclude that more than 50% of students in our survey take online courses? Assuming that You're an online reporter. Write a brief statement that accurately describes the results and include all the relevant information. So what's the first step? Well, first step, does it satisfy all the conditions? Check that the requirements are satisfied. So is it a fixed number of trials? What's the number of students surveyed? Yeah. 950 students. Check, it's fixed. Are the trials independent? Yeah, because each student answered their own survey. That's independent. Only two possible outcomes. Yeah. Yes, no. To take online courses. That's 50%. All right, only two possibilities. The probability is the same, yes. So it satisfies all that. Find the E. So what's the formula for E? Okay, so what do we need? We have to first find the critical value. So it's 95%. So now we have 95%. What do we do with that? One minus 0.95. Now what do we do? Look at your notes. We just did it not too long ago. Since we're 95%, that's 0.95. 1 minus is 0.05 divided by 2. Remember what this represents. This is 2.5. 2.5 plus 95 is 97.5. We look at 0.9750 inside the chart. And what is that going to give us?
That's 1.9.
6.
5,
Yes.
6.
Yes. Okay, so now we have N. N is the number of surveys we did. Is 950. What's P hat?
Mm,
Anybody
95.
else? What's that? P is success. 53% took online courses, so P hat is 53%, which is 0.53. How many people did not take online courses? 47% or 0.47. So it's 0.53 times 0.47. Calculate all this stuff. It's going to give us 0.0317381. Remember, do not round any of your numbers until the very end. Use everything the calculator gives you. So this is my E. So what I have to do here is I got to take my P hat minus E and my P hat plus E. So what's P hat? 0.53, that's our success, minus our number 0.0317381 is less than P is less than 0.53 plus 0.0317381. And now at this last step, that's where we rounded up to 3 decimal places. So 0.53 minus 0.03173 will give us a solution set of 0.498 to add the other side is 0.62. Because if we look at this, if we look at these two numbers, remember, our P hat was 53%. And our error is 0.0317381, which becomes 0.032. So our error is approximately 3.2%. And if we look at this, so we have 53 minus 3.2, 53 plus 3.2, we'll get 49.8, 56.2. Which is what we pretty much found out there. Okay, so that. Can we safely say that more than 50% of our data falls between there? This is question 3. Can we safely conclude that more than 50% of students take online classes? So look at it. This one's saying 50%. This one's saying 49.8 and 56.2. So that's pretty close. That's too narrow. So we can't safely say it because this one's only 0.2 away. In other words, if 2 students stop taking classes, we're below there now. So no. Because 49.8 is too close to 50% to be confident. Okay, and what's our last one? Conclusion. And this will vary from student. Remember what the notes said earlier is how you would read, how you would state that. So pretty much just mirror what that statement was. So 53% of online undergraduates students take online courses. Based on the Sallie Mae survey results of 950 randomly selected students. It was found that with a 95% confidence or level of confidence, at 49.8% to 56.2% of the students take online courses. So with that interval, being so close to the 53%, we found that 3.2% change in either direction would result in an unfavorable solution. But yeah, you can vary what you put in there. So it doesn't matter what you put in. I mean, so yeah, it varies on what you put in there, on what's asking, and finding the point estimate and E from a confidence interval. So if we know the confidence interval, then to find the point estimate P hat, we will need to we use upper confidence limit minus, or we're going to average them, so lower well, this is upper the confidence interval. So we have our plus or minus E. That's what that gives us. So we add them together, find, put them and divide by 2. That finds us our population mean or our population proportion. Let's think about it. If we had 3 is So if we had our confidence intervals this 3 to 7, this is be our upper. This is our lower. So 3 plus 7 divided by 2. That tells us the middle number. Because what that's going to tell us, it's going to, well, we could determine from this, but now to find the margin of error, E, we take the same values, but this time we subtract them. Upper confidence limit, lower limit. So looking at this value here, this is our P. So if that's 5, what do we have to do to find 3? How do we go from 5 to 3?
Do we subtract?
Well, I was in the next round ask you how do we go from 5 to 7? Because remember, the interval is P hat minus error, P hat plus error.
Plus error.
So if this was 5, how do we get to 3? It's not rocket science. In elementary school, you learn this. Hold up 5 fingers. How do you get 3 fingers? What do you have to do?
You take away 3 from 5.
No, we take away 2 from 5. How do we get to 7? We add 2. So the error is going to be 2. To go from 5 to 3, we subtract 2. To go from 5 to 7, we add 2. So 2 is going to be our margin of error. Well, let's see. The upper confidence interval is 7. Lower is 3. Divide by 2. 7 minus 3 is 4. That is your error, which we can figure it out just by looking at the finding our values. So let's look at example 3.
So sorry, Professor, what did you get at the final answer there?
3
For
or
that example 2.
2. The margin of error is 2.
Margin of error is 2.
Yeah. Because the upper bound is 7, the lower bound is 3. 7 minus
Okay.
3 is 4 divided by 2.
Okay.
Okay,
What of
example 3.
what of the 5? What did we do to the 5?
That was just an example I gave because we know what the bounds are going to be. We know that the upper bound is 7, lower bound is 3.
It's 3, yeah.
So we can extrapolate to find the population proportion because it has to be exactly halfway between the 3 and 7. Finding sample proportions and okay. Finding sample proportions and E, margin of error. The article High Dose of Nicotine Patch Theory. Of 71 subjects, 70% were abstinent from smoking at 8 weeks using a 95%, bless you, confidence interval. $58 to 81. This is all we know. Use the statement to find the point estimate and the margin of error. The point estimate is p hat. So these are our formulas. What it gave us was of the 71 subjects, 70% were abstinent from smoking. At 8 weeks, with a 95% confidence interval, we found out that it ranged from 58% to 81%. So that's my lower to upper bounds. Upper is 81%. Lower is 58% over 2. 81% minus 58% divided by 2. So it's 139 over 2, which gives us 69.5%, which is 0.695. And the difference is 81 minus 58. So we have 81 minus 58, 23% over 2, which is 11.5%, which makes it 0.115. So my sample proportion is 0.695. And my margin of error is 0.115. All right, so it's just straightforward in those formulas. Using confidence intervals for hypothesis testing. What is a hypothesis? It's not educated. Yeah, people say that, but it's not really. Hypothesis is a idea you have based on observation. Kids have them all the time. When you're walking and kids see in fall time, what happens to the leaves? They used to be green in the summer, now they're turning brown. Why? Why do they start falling off? That's a hypothesis. Hypothesis is explaining why. What's my guess? It is, you said that's where I say educated guess. So it's something you can now, we have to go as something that you can now physically compare. So for example, a confidence interval, let's say it's between 3 and 7. From there, we just determined we could figure out our proportion sample, and we can figure out our estimate error, which we're going to need those. We can't really do hypothesis testing just yet because we have to go through and now determine what is a hypothesis, what is the null hypothesis, what's the alternate hypothesis, how do you compare the two. So the first thing we got to do is determine the sample size. Sample size is n. Let's look at both of these equations. So what we can do here is if we have the confidence interval, we can find p hat. How do we find q hat? That's error. You're close. Remember, p is a sample proportion of success. Well, 1 minus success is what's left is failure or not success. So now we have the numerator there. We can figure out the E by upper minus lower divided by 2. We have to have the confidence interval because we have the z-score. So this is going to be given, or we can calculate given alpha. So now we have to solve for n. And that's a whole algebra process. I mean, it's not that difficult. What we could do is here, what we would do, instead of putting this, I'm gonna leave it as E. So we have E is equal to Z P hat Q hat, because it's gonna. So the first thing we have to get rid of Z, because we're trying to get the n by itself. So we multiply or divide both sides by Z. Because it's multiplied, so we have to do the opposite. So we got E over our z-score. Remember, we're trying to get to n. So we have to get rid of the square root. The opposite of the square root is if we square both sides. So the square root and the square cancel. So we have e, well, we can distribute that. So we have e squared over z squared equals p hat q hat over n. Since it's a proportion, I need to have n on top. So I can flip this, which means I got to flip this. I want to get n by itself. I have to get rid of this. How do I get rid of that? Since it's on the bottom, multiply both sides by it. So n is equal to z squared p hat q hat over my so if p hat is known, great. If we can calculate, great. If not, then we can go any further. But we have to know the confidence intervals. We have to know the upper and lower bounds. That's how you determine sample size. It's very algebraic, yes. There's a table.
Professor, please can we continue tomorrow?
Or no, I'm almost done. Yeah, you can log off and I'm gonna send the video. Well, I've got a couple more pages to cover. But the requirements to do that, to find the n, the requirements. Sample must be a simple random sample. Each event must be independent. Which is what we said earlier also. So the round off rule for computing the sample size n is round up to the next larger integer. So once you do all your calculations, just round up. Example 4. What percentage of adults make online purchase? A Pew research in 2016 said that out of 4,787 randomly selected adults, 79% said yes, they do. Assume that 79% make online purchases, and assume no prior information known. Okay, so we're gonna use a 95% confidence interval. If we have a 95% confidence interval, what's our alpha? Yeah, it's 95, 1 minus 95 is 5%, which is 0.05. So it's 0.05. If that's our alpha, what's our Z alpha over 2? Which is Z 0.5 divided by 2 is Z of 0.025. I mean, these are, and that's why we did those charts earlier, because they're always going to be the same. At 95,
Is it Z is 0.5 or 0.05?
this is 0.5, 0.05. There's your alpha. So it's 0.05 over 2, which is 0.25, makes it 1.96. That's our Z value. And our error, factor E, margin of error, was 3%. So what would P hat be? Remember, 79% said yes, we're looking for how many people shop online. So P hat would be 79%, which is 0.79. That means Q hat would be 1 minus 0.79, which is 0.21. Remember, we're finding N. This is what's stated. We calculated that. We have our formula for N. Using N equals our Z value squared times P hat Q hat over our error squared. We have 1.96 squared, 0.79, 0.21, all over 0.03 squared. And put that in your calculator, you get so our N rounded up to the next biggest integer. Why do we round it up to the next biggest integer? Because remember, the rounding rule, if it's a 1, we should just drop that off. But because our sample size has to be bigger than 708, even if it's 0.01, we have to round it up to the next higher number. Because that way we could be sure to have enough. So that's our sample size. Okay, the second part. It says assume no prior information is known. No prior info is known. So we have our formula. Now, since no prior information is known, let me make sure I read that correctly. Yes. We do know our Z value, which is 1.96. We do know our error value is 0.03. We just don't know anything about P hat and Q hat. What we're gonna do here now is, because if you look at our bell curve, we have those. There's Z1, Z2. And anyway, it's cut in half. So we have 4 areas. So we know that each one of these are 1/4. So that's why we use 1/4 here. Since we don't know for sure, we know it's going to be 1/4 accurate, which is 0.25 in decimal. And plug that in there. We'll get 1067.11, which is 1068. So since we didn't know anything, to be safe than sorry, we now need 359 more people. That's our sample size needed. Since we had no information about our population. All right, well, that's about it, because the rest of it we can cover tomorrow. It's just pretty short. There are no more examples, really. We'll just talk about a couple more methods. Okay, sorry it's so long. Thank you for waiting. And we'll do 7-2 tomorrow. Now, if it